Once again, I'm very happy to be able to talk to you about the research that we've been doing here under the BRT Center of Excellence's current iteration of funding. So we've been looking at paratransit from various angles over the last few years, and in the last couple of years, we've been looking specifically at the electrification possibilities and feasibility of transforming or using electrification as a way of helping to transform the informal industry within South Africa. I want to start by just briefly talking about what's been happening around electrification of public transport in Africa in general. There's a initial interest in specifically the bus industry in deploying electric buses. Senegal, Dakar just launched its BRT with 100% electric fleet, and there's been other operators in Rwanda, for instance, that have been going towards electric buses. In South Africa, one of our big bus operators are slowly rolling out electric buses, around 60 per year over the next few years. So there's been a bit of experimentation around this and a very kind of slow uptake in electrification in public transport. I think within the informal part of the public transport industry, there's been some other interesting things happening, for instance, around the use of motorcycle taxis. So Kenya, for instance, starting to manufacture electric motorcycles, and particularly to be used in their boda boda or motorcycle taxi industry, with some government support there. In South Africa, of course, like in many other countries in Africa, the biggest informal mode is the minibus taxi. So we have a fleet of about let's say 200 to 200,000 vehicles nationally, and we've sort of deployed one electric taxi in a testing kind of mode. There's been a lot of talk about electrification, but actually very little movement in this direction. And if one looks at the numbers of these informal minibuses and buses of various sizes being used all over Africa, and you can think about the electrification of these vehicles, there might be quite a significant greenhouse gas benefit that could come from turning them over into less polluting, low fossil or fossil fuel free kind of vehicles. It could also be particularly useful to convert these vehicles, because they are often driven quite intensively. So you have a lot of kilometers that you will be converting into lower emission technology by addressing informal public transport, more so than just passenger vehicles on a daily basis. And also these vehicles are often not very well maintained, and they are dirtier than the average passenger vehicle. So it might be a very efficient way of getting to some of these climate goals that we've been talking about. And so transforming vehicles into electric fleets, might contribute to modernizing these fleets, and might be part of the narrative of modernizing and deploying new fleets of vehicles all over the continent, and that's something that's happening already. It's particularly on the cost side where some of the arguments or the opportunities for electrification might be attractive. Rising energy prices in energy is in these informal fleets within Africa the biggest cost element, and because of instability of cost prices, going to electrification might actually be quite attractive from a cost point of view. And so there are opportunities there that could be captured as well. So just kind of briefly, some of the key knowledge gaps that we see in this discussion around how do we move towards electrification, or should we even move towards electrification of paratransit within Africa. There's very little work that has actually been done in this area, a little bit, but there's a lot that needs to be figured out. So the first uncertainty is, of course, around the development of technology. Many potential technology pathways available, and hydrogen versus battery electric versus hybrid and so on. So those kind of things create uncertainties around where to go with this. Then around, of course, the issues of cost and the financial impacts of these technologies on, firstly, the operators, but also the users. There's a lot that needs to be researched in that area. The issue of technical compatibility. So paratransit, of course, operates very differently from formal bus routes, and that raises lots of interesting questions about how compatible this kind of mode is with the technical requirements of a battery electric vehicle, for instance. Issues around charging, issues around ranges, and so on, which will look very, very different from the formal bus system and work that what we've learned in that industry. And then, of course, the issues of perception and whether owners of these vehicles and also the drivers are willing to make the switch and willing to adopt. Those are sort of questions that have started to be looked at. The paratransit industry, informal operators tend to be quite risk averse because they are, in almost all cases, completely privately funded, no subsidies in there, and often with quite low margins, so quite conservative in their adoption of new operating patterns and new technology. So how that will play out in terms of the willingness to adopt is an interesting question for research as well. Then on the wider impacts, the issues of electricity availability and the impact on the grid are particularly relevant in some countries, for instance, in South Africa, where we have big problems with insufficient electricity supply nationally, and whether we can, it's funny that we're talking about massively expanding electric vehicles at a time when we actually don't have enough electric power available in the grid for even just day-to-day national activities. So that is a significant issue, and of course the questions around whether one can use renewable energy as part of this are then also raised. And then lastly, regulatory and industrial policy impacts. So how do we deal with these kind of changes? Those kind of questions, especially in the paratransit industry, need to be looked at. And underlying a lot of these knowledge gaps is, of course, the issues related to not having enough data to actually ask these questions and do research on it. So that's slowly changing, but there are certain clear problems around just having the data to be doing this research. So the work that I'm going to be talking about very briefly here is work that we've been doing to look at the technical compatibility issues. So the question of whether and how the particular operating conditions of paratransit are conducive or make the mode conducive to being electrified. So the method that we've been using, we've been asking the question: can we estimate the potential energy requirements of battery electric minibus taxis under real-world conditions? So particularly battery electric at this stage, and we particularly want to look at what it would take under real operating conditions to actually electrify some of these vehicles. We've been using at this stage a simulation approach using software called EV Fleet Sim that was developed by our colleagues at Stellenbosch University, and we've been helping to refine and change that. The software has not been tested on large data sets, so we're adding that by looking at a lot of data on current operating patterns, assuming that the taxis that have been tracked do not change their operating patterns, their routes and their times and so forth. As a starting point, we might change that later on to look at optimizing their operating patterns. There is tracking data that we managed to find for Pretoria, Tshwane, the city that we are in, that we find very useful. There are various initiatives around Africa, various cities, to collect a lot more data on paratransit or informal operations. Several data sets of tracking of small sets of vehicles that have been done and that are being made available to researchers. So there's some promise there in getting better data on real-world paratransit operations within African cities. So the simulation tool, just kind of briefly, EV Fleet Sim runs on Sumo, which is an open source micro simulation package that is linked to a street network, and then per minute data of vehicle movements. Actually, it's not just per minute, it's also per second data of actually tracked vehicles that get simulated in Sumo. It's connected to an energy model, a kinetic energy model that then estimates the movement, the energy requirements on a 1 Hertz on a second by second basis, and that is then output in various formats, and I will show you some examples of that. Oops. So just about the sample that the data on the sample that we've been looking at, we have data collected from about 205 vehicles that were tracked over between 3 and 5 days. This was a number of years ago, but still relatively representative of the current situation. And the vehicles, the tracking data includes quite detailed data then on vehicle stops, on the routes that they take, on the various trips that they make over these multiple days, and so forth. So it's a very rich data set that we can use. We have focused just as a starting point to get it going just on 8 taxis, and we've looked at 2 types of groups. So we found that it's quite useful to differentiate between what we call ex-urban and urban types of operations. So ex-urban are longer distance day-to-day kind of commuting patterns, for instance, from some of the outlying residential areas, taking 30 or 40 kilometer trips into the CBD area here. And the urban type of operations are much more concentrated within the denser part of the city, where taxis make, let's say, 20 to 24 trips per day on average. So a lot more trips that, round trips being made, but these trips are shorter distances. And interestingly, in both the ex-urban and the urban types of operations, taxis have more or less the same daily range, but of course, how that's distributed across the day could vary quite significantly. Some of the limitations of this sample and of the data, the simulation that we've done, is that the routing is simulated and doesn't always 100% correspond to the data that was all the minutiae of the routes that are taken. Sometimes there's some deviations. And we don't have an actual traffic model connected to this to simulate or estimate speeds. We are, at this point, only estimating speeds from the tracking data for the vehicles. Okay, so these are some of the outputs that one gets from the software, from the simulation. Firstly, the energy use on an instantaneous basis across the day. You can see the distances that were estimated and tracked here for the different vehicles. You can, for instance, see that there's quite a range of daily distances between the 8 vehicles that we have selected. Some vehicles doing, let's say, 80 or so kilometers per day, and other ones doing almost 300 kilometers per day. And then also the average power usage of vehicles across the hours of the day. The blue line here is the average, the mean for the 8 vehicles, and then you can see the distribution in the shaded area here. And you can see that there's quite a big variation in the amount of power used by the vehicles at various times of the day. So quite a wide range of energy requirements for these 8 vehicles. But clearly, they peak here in the morning and the afternoon, as one would expect. The key question, though, is not around instantaneous power use or energy use, but more about battery charges, battery capacities, and the total amount of energy required during the day. And the graph that you see here shows the daily energy usage then for the 8 vehicles. You can firstly see that there's quite a wide range. Some of the vehicles use very little energy across the three to 5 days that they've been tracked, and other ones use much more. So there's quite a wide range of energy needs that one finds within this fleet. And we didn't set out to look at vehicles with large variations in energy requirements. We looked at vehicles with variations in operating patterns, and we found that, of course, these things are correlated, as you would expect. So on average, around 130 kilowatt hours per day for these taxis. Now, the current battery capacities that we find in the market range between, let's say, 60 to 120 kilowatt hour batteries. Of course, that's changing fast, but it really means that the average vehicle in this little test fleet that we looked at do have more high energy requirements in a day than what they can typically get from a battery, but only slightly more. So that might then change over time. And that really means that most taxis would need recharging during the day. So they can't just charge at night and then have, with one single set of batteries, be able to make it throughout the whole day. So we need to look at recharging at key periods during the day as well. That's one of the key results that we find. So looking at these charging opportunities, of course, so we looked at the downtime of the vehicles that we have. You can see some of the vehicles, all the vehicles have quite a long downtime at night. So 7 of the 8 minibus taxis stop for at least 7 hours. So that's a good time to charge batteries, as one can expect. During the rest of the day, some vehicles have multiple periods of short times that they are inactive, and other vehicles have longer periods during which they're inactive. And a lot of this is all correlated to the type of operation. So the ex-urban taxis, the longer distance taxis, they typically have the longer downtimes during the day because they tend to operate more in the morning and the afternoon, peak commute periods when people make these trips to and from work. The urban taxis look a bit less promising in that sense because they tend to have very short downtimes in the middle of the day, and just three of the 4 taxis would have insufficient downtime for doing that recharging. So the conclusions, what we take from this, it's a sort of beginner study. We're expanding this. What we've learned up to now is that we do need quite a lot of very detailed data to estimate the potential for electrification, and that data is a problem. And we would have to invest better to get better data to actually be able to really answer planning and infrastructure and market feasibility kinds of questions around electrification in this industry. We need data with a lot of granularity and, of course, complete data that would give us insight into a vehicle's movements across multiple days, not just during the times when it's actually ferrying passengers. The software tool that we used seemed to be quite useful for that. We're working on improving it in various ways. The sample of taxis that we looked at up to now shows that that some taxis are likely to be more suitable to electrification in terms of their total daily energy use, what can be delivered by the batteries, and also how much time they have available for recharging during the day. So we're cautiously optimistic that there is a case to be made for at least some part of the fleet to be electrified, even with current technology, but most likely not all paratransit vehicles within South African cities and maybe even outside of South Africa as well. But that's with current operating patterns. So if we assume that if we don't assume that current trips and routes and operating patterns must stay the same, but that they are able to adapt to this new technology, then the picture might change a bit, and it might expand the feasibility of these services. In what ways these services or these operations will adapt to a new vehicle technology and what is required for that is not something that we quite know at this point. One of the key other findings that we have is around, of course, the grid impact. So if you scale up the results that we have here to the 250,000 minibus taxis within South Africa, or even just say, let's say, the 150,000 or so that are operating in urban areas, you have much more electricity required than what our system can offer at this point. And of course, the system, the electricity supply system in South Africa is about 90 to 95% coal-based, so it's very dirty electricity. So in terms of greenhouse gases, we're not really going to be doing anything good by doing this kind of electrification. So that's, of course, the big problem, the big issue with all of this is probably much more a long-term kind of conversation around transformation of the whole energy electricity system within our country and other places. So some of the ongoing work that we are still doing on this, we're looking at the question of charging infrastructure and the placement, the location of charging depots, and then the financial issues around infrastructure, around vehicle procurement, and the long-term energy costs. Right, thank you to my collaborators on this project, some of them from Stellenbosch University, and Salma Abdelgader, who's a student at TUX, at the University of Pretoria. And my email is there in case anybody wants to get in touch. Thank you.